Things take up space. You take up space. Cars take up space. Mountains, they take up space. There's just no changing that. But in our world, there's only so much space to fill, which is a lesson most of us have learned the hard way. Like when you learned the beautiful new queen-size bed you bought takes up a bit more space than you planned. Just me? That's fine. Understanding how much space objects take up gives us the ability to plan ahead. Whether we're deciding if we can upgrade to that new luxurious queen-size bed, or if we're designing a parking lot, we need to know how much space we're working with. This episode will figure out how to calculate the amount of space inside different two-dimensional shapes, so we're ready for any mattresses life throws our way. I'm Jason Guglielmo, and this is Study Hall Real World College Math. Nikema is an event planner who wants to throw an event for Disability Awareness Month for the week after the march we planned last episode. Most importantly, she wants to make sure things don't go like they did last year. One of her first tasks is making sure they have a location with the right amount of space. Basically, Nikema wants to make sure there's enough park space to accommodate attendees, vendors, water stations, and a stage that needs to be big enough to hold seats for various community leaders. And to do that, she needs to examine the different relationships and patterns between different geometric objects so she can apply what she's learned to this real park dilemma. Last episode, we dealt with perimeter, which is the length of a line or boundary that goes around the outside of a shape. Now we want to focus on the space inside of a shape. We call this the area, and in technical math term, it's the amount of flat, two-dimensional space that's taken up by a shape or object. Fortunately, Nikema already has some ideas, and she thinks 4 Greensboro Corners Park is the perfect location. Including the parking lot, the park is enclosed by 2 pairs of parallel streets with 4 right interior angles. This means 4 Greensboro Corners Park is in the shape of a rectangle. But to make sure it's big enough for the event, we need to check the area. One way to do this is by putting a grid on top of a map of the park where each square is 1 yard by 1 yard. We'll use these squares as our units for area and call them square yards. By simply counting each square one by one, there are 154 square yards within the bounds of the park. So the area of 4 Greensboro Corners is 154 square yards. But counting a bunch of squares is a lot of work and isn't really practical in real life. We can make the process a bit easier though. Notice there are 11 squares along the side and 14 columns along the bottom. Those match how big the length and width of the park are in yards. That means we can simply multiply the width and the length to find the area, which is something we can do for any rectangle. 14 times 11 gives us 154 square yards. Now, finding the area of a rectangle might not be new information for everyone, but it's a good tool to have in our back pocket as we try to tackle more complicated shapes. For instance, Nikema's co-organizers point out that the parking lot needs to remain open for accessibility reasons. So we need to know how much space is available without including the parking lot. The park's new area isn't quite as easy to calculate, but we can break it into 2 smaller rectangles that are easy to calculate. The top rectangle has a width of 14 yards and a height of 4 yards. So, based on our previous thinking, the area is 14 times 4 square yards. The bottom rectangle has a width of 8 yards, but the height will take a little extra work. The entire height for that side is 11 yards, and the height of the top rectangle is 4. Opposite sides of the rectangle are the same length, so 11 minus 4 is a height of 7 yards. That means the area is 8 times 7 square yards. Add those 2 areas together, and the park has an available area of 112 square yards. So, even just knowing how to find the area of a rectangle, with a little critical thinking, we're able to find the area of a whole array of wonkier shapes. For instance, knowing the available area of 4 Greensboro Corners is helpful to Nikema, but she also wants to consider some other options. Specifically, the other location the organizers want to consider is Graham Park, which is shaped a little differently from 4 Greensboro Corners. Graham Park is also surrounded by 4 streets. And like 4 Greensboro Corners, it has 2 pairs of parallel streets. But it has a bit of a slant to it on the west and east sides. Since each pair of opposing sides are parallel to each other, we call this a parallelogram. If we overlaid our grid on this parallelogram, we wouldn't be able to just count up the squares like we did with the rectangle. But we can still use what we know about rectangles and area to help us get started here. Let's say the street at the bottom of the park is the width of the park's shape. Making a dashed line from the bottom straight up to the corner of the park's boundary reveals the length of the park to be 4 yards, and we can see two shapes, a triangle and another wonky 4-sided shape. Now we could try to find the area of these shapes, but imagine sliding that triangle to the right side of the parallelogram. Boom! Now we have a rectangle with the exact same area as our original shape, and we can find the area the same way as before. The width of this shapeshifted parallelogram is still 14 yards, and the length is 4 yards. Multiply the length by the width, and we get an area of 56 square yards. And now that we have both areas, it's clear to Nikema that 4 Greensboro Corners is the better venue since it has a much larger area available than Graham Park. But the size of the park isn't the only thing they need to figure out. Last year, the stage took up half the park, and that really limited the rest of the event. So now Nikema and her team need to pick an appropriate stage shape for their speakers. The stage has to be small enough to fit within one of the 2 rectangles at 4 Greensboro Corners Park. But it also has to be wide enough for speakers to be able to walk back and forth on stage and fit all of the sound equipment and chairs that will be in place. And based on her research into stage rentals, there are 4 options. The first stage option has 4 sides and only one pair of sides that are parallel to each other. We call this type of shape a trapezoid. The trapezoidal stage has a length of 5 yards. Since it doesn't have a consistent width from top to bottom, we'll look at the dimensions for both its sides instead. It has a bottom base of 7 yards and a top base of 4 yards. But since it has 2 slanted sides that aren't parallel, calculating the area to make sure it will fit in the park won't be as easy as the parallelogram, where we just slid a triangle over and a rectangle appeared. But we can still use the power of rectangles to figure this out. In order to cut our trapezoid into helpful rectangles and triangles like we did with Graham Park, let's first cut the trapezoid in half horizontally. That should give us 2 new trapezoids that are each 2.5 yards tall. And if we draw another horizontal line here, its width should be the average length of the top and the bottom, which comes out to 5.5 yards. This midline comes to the average of the top and bottom because as we move from one side of the trapezoid to the other, the lines bend in at a constant rate. So when you get halfway through the shape, you should be halfway between the lengths of the 2 sides, which is the average. Now, let's find any rectangles we can. If we draw 2 dashed lines on either side of the midline we just drew, rectangles and a few triangles start popping up. Just like before, we can arrange those pieces to form complete rectangles. For these 2 new rectangles, the width is the average of the 2 original bases, and the length is half of the original trapezoid's length. We can multiply the width of each rectangle times the length and multiply it by 2. And if we swap in our letter labels and simplify a bit, we end up building a formula that works for finding the area of any trapezoid, just based on what we already knew about rectangles. For this stage, that means the area it takes up is 5 times 7 plus 4 divided by 2, which is 27.5 square yards. So yet again, with some geometric ingenuity, we could use the basics we're familiar with to come up with new mathematical ideas. But the trapezoid isn't our only option for a stage. The second and third shape options for the stage are both triangles. We already saw a few triangles in our last example, but formally a triangle is any closed 3-sided figure with straight sides. And just like the other shapes, we can also find the area of a triangle by relating it to a rectangle. Similar to trapezoids, we'll talk about these in terms of their base and height, which are basically just width and length, but the terms are a bit different. The first triangular stage option has a base of 8 yards and a height of 4 yards. Now, rather than slice up the triangle like we did before, let's encompass this triangle in a rectangle that touches at the edges of the base and the very top. This way, we don't end up with more little triangles inside the triangle we already have. There are 2 rectangles we can see now, one on either side of the peak of the triangle, and both rectangles make an even larger rectangle together. And if we focus on each individual rectangle, the portion of our original triangle takes up exactly half of that rectangle. And based on that, we can see that the entire original triangle takes up half of the space inside the larger rectangle. When dealing with geometry, and even looking for patterns and solving problems in other areas of math, It can be helpful to make observations like these, because here the formula is actually in our own words. We know the space inside any rectangle is length times width, and the triangle is taking up half of that length times width space. So the area formula for a triangle is 1/2 times base times height. So for this triangle stage, the area is 1/2 times 8 times 4, which is an area of 16 square yards. Next, the other triangular stage option looks like this. What makes it stand out is that, well, we can't really tell which side is the base of the triangle or what is the height. It's just a triangle. We just know how long each side is. Since we only know the length of each side, we have to use a different approach, which involves something called Heron's formula. Each side length will be labeled A, B, or C, and it doesn't matter which is which. So 8 yards, 7 yards, and 6 yards in this case. Then S is the semi-perimeter, which is half the sum of the side lengths. Here on Study Hall, we'll rarely give you a formula without explaining where it comes from. But Heron's formula is a bit complex and deals with ideas we haven't covered yet in this series. Here's an annotated explanation if you want to pause and check it out. But for now, we're using it here so you have one more tool to use if you're not able to rely on what we already know about rectangles. So, using Heron's formula, the area of this triangle stage is approximately 20.33 square yards. Finally, there's one last stage option that's even more innovative than the last: a circle. Circles aren't like the other shapes. They're not made out of line segments, and we can't cut them into pieces to neatly make them into rectangles like most of the other options. So here we'll have to get more creative to find the area. Like before, we can start with a shape we already know how to calculate the area of. So imagine a circle inside of a square. There's a lot of empty space around the circle, so we can shrink that empty space by turning the square into a shape with more sides, like an octagon. And the more sides we add, the more that space shrinks. Now imagine turning each side of the octagon into a triangle, with the center of the circle as one corner. The height of each triangle would be the same length as the radius, which is the length from the center of a circle to its edge. And the area of that triangle is 1/2 times the side length of the octagon times the radius, because the base of that triangle is the octagon side and the height is the radius. Now, there are 8 of these triangles inside the circle. So the area of the circle would be about 8 times the area of each of these triangles. Now, what if we turned our octagon into a shape with more and more sides? The shape would get closer and closer to being a circle, and we'd get closer and closer to the actual area of the circle. Writing that math down is a little beyond this course, so instead let's make some observations. The formula we have so far is 1/2 times the radius times 8 times the side length of the octagon. Well, the perimeter of the octagon is also 8 times the side length of the octagon. So how about we just swap the perimeter of the octagon for the formula for the perimeter of a circle, which is 2 times pi times the radius. Simplifying that, the 1/2 and 2 multiply to be 1. So the formula for the area of a circle ends up being pi times the radius squared. Again, we skipped some steps, but this is essentially one way to arrive at the area of a circle. Applying this to Nakima's stage problem, the circular stage they're considering has a radius of 2 yards. So the stage would take up an area of pi times 2 squared, which is approximately 12.5 square yards. Putting all this stage information into a table, Nakima decides to go with the trapezoidal stage since it is the largest possible stage size of all the ones that could fit. I don't know about you all, but I'm feeling much more in shape after working with so many different rectangles, triangles, trapezoids, and circles. See what I did there? But seriously, understanding how different shapes fit together and how space is allocated and divided can be essential information. And while it may seem basic, many times space can be broken down to easier chunks, which can just be smaller yet more familiar shapes. Geometry really is a powerful tool for understanding our physical world, which we'll explore more next time when we step into the third dimension and calculate surface area. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.